All right, so we've been looking at integration exclusively, right? So we're still in chapter 8. We're going to do only one more unit before Christmas. So I'll just give you a couple quizzes before then, of course, and probably an opportunity to improve your grade. But 8 and 9, we're going to kind of combine this last part of chapter 8 and the first half, or a little more than half of chapter 9, and we'll call it good at Christmas. There's a natural breaking point in the middle of chapter 9. So chapter 8, the last thing that's in it is what are called improper integrals. Those are integrals that involve forms of infinity. When you're integrating up to the edges of asymptotes, what do? And when you're integrating in other strange places, what happens? So before we get into that, that's what we'll look at next week. I thought we'd go back and review some indeterminate forms, and that's kind of what's in 8.7. So I think it's nice, and it's got some indeterminate forms you have not seen before as well. So we're going to take stuff that we know about indeterminate forms and take it further. Which ones of those, or one of those, is indeterminate? 0 over 0. So we know that 0 over 0 requires special mathematics, right? If you ever have a limit work out to 0 over 0, or what's the other most popular indeterminate form you guys have seen before? Infinity over infinity. That's an undecidable thing unless you use clever algebra or a big machine called, it's really a small machine, but it's called L'Hopital's rule. So we're going to see L'Hopital's rule come up, but we're going to see that there are other forms that are undecidable or indeterminate as well. So I just thought we'd go back to the real basics before we talk about some of those indeterminate forms, okay? So 12 divided by 3 is, of course, 4, but there's another way to think about that, right? Why? Because one way to think about that is because 3 times 4 equals 12, right? If you think about it with inverses. 0 over 7 is what? 0. One way to think about that is if you have nothing and you cut it into 7 pieces, well, you still have a whole lot of nothing. But another way to think about that is to think of it as a multiplication. In fact, what? 7 times this 0 equals that 0. And of course 7 times nothing is still nothing, right? So what's 4 divided by 0? That we call undefined in mathematics. Why? Well, there's different ways to think about that. You could think about it as, if I have 4 pizzas and I cut them into pieces of size nothing, where do I cut? Right? I've encouraged you guys to think like that before. But another way you can think about it is a multiplication problem. What multiplication problem is this? So instead of saying undefined, let's just say question mark. 0 times question mark equals 4. What do you put in that question mark? 0 wipes out everything. It can't make something into 4. And that's really why that has no definition. So there's another way to think about it. So when you have 0 over 0, we call that question mark as well, except this question mark you're never going to be able to resolve. This question mark you can resolve. It just depends on what 0 over 0 came from. You can use clever algebra or L'Hopital's rule or other mathematics to resolve that. The thing is, sometimes it's equal to 7, sometimes it's equal to negative 2/3, and sometimes it's equal to infinity. It really depends on where it came from, if it's an indeterminate form like that, okay? So I just wanted to review some simple indeterminate forms with actual math, so I've got those over here on my left. So can you guys tell me, do you remember how to do this limit? There's many, many ways to do this limit. What's the answer? Derek? 2. If you just plug infinity in, you'll get 2 times infinity plus 1 is obviously infinity. And down on the bottom, infinity minus 7. Infinity doesn't care about 7. It says I'm still infinity. That's indeterminate. It's infinity over infinity. So you can apply L'Hopital's rule, which says take the derivative of the top function, which is plain 2, and the derivative of the bottom function, which is 1. And what's the limit as x approaches infinity of 2 over 1? It's 2. You could also think about this as an asymptote problem, right? This is a rational function, and its horizontal asymptote coefficients are equal. So the asymptote is y equals the ratio of those coefficients, right? There's all kinds of different ways. You can play with clever ones there to get that same answer. All kinds of different ways to get 2 as the answer there. But my point is, this is basically, before it's equal to 2, it was equal to what indeterminate form? Which eventually becomes 2 by whatever reasoning you pursue. Pre-calc with asymptotes, more advanced calc with L'Hopital's rule, or you can use a clever one and go 1 over x, and get it to come out that way too, okay? But my point is that infinity over infinity is 2. This one's also infinity over infinity, isn't it? But it's not 2. It comes out to 3/4. So, just a little review of indeterminate forms, right? That's the idea, is that it depends on where the indeterminate form came from as to what it really becomes. Yeah? There's other indeterminate forms in math. So let's just do a couple review problems with L'Hopital's rule, and then we'll get to some of those. In fact, let's just look at some of those first. I think let's do it that way. So here's another indeterminate form. We're going to see all kinds of them. Here, I'll just write some of them down. 0 times infinity. What's that? 0. Maybe. Maybe it's 7. Maybe it's infinity. It depends where it comes from. So if you ever run into this, what you're going to have to do with it is turn it into one of the indeterminate forms we've seen and do algebra with it, like maybe L'Hopital's rule. So we'll see one like that today. That's indeterminate. Infinity minus infinity. Sometimes that's 0, sometimes it's still infinity, sometimes it's 8. It really just depends. These are all just other kinds of indeterminate forms. Here's another one. This one I think is probably the least intuitive of them all. And these are not this is not an exhaustive list of all indeterminate forms either. 1 to infinity you'd really think is 1, because 1 to any other power is 1. But no. So let's investigate that one. Got your calculator? Grab your calculator. That's why I've got mine on. So let's look at some different 1 to infinities. How about this one? And this is all building up to one of the last big concepts we're going to really be working with this year, which is chapter 9, which is all kinds of different infinite ideas with series and sequences, which is my favorite part of Calc 2. Integrals are fun, but series is where it's at. So I'm going to write down 3 different problems. We're going to look at 1 or 2 of them together. And the other one I want you guys to resolve on your own before tomorrow's class period, okay? So we'll do the first couple of these. And the other one I want you to do yourself. So that first one should kind of look familiar. We're going to be investigating that over the course of today's lesson. I've thrown that on the board before in your past. You probably just have forgotten about it, which is fine. The other ones are things you haven't really seen before. But all of those, if you try to evaluate the limit, become what? Put infinity in. What's 1 over something really, really big? It goes to 0 if you actually go to infinity. So that's 1 plus 0. 1 to infinity. Right now, this is the indeterminate form 1 to infinity. Is it not? That one is the same thing, is it not?
Yes.
Is that one the same thing? 2 infinities, though, is infinity. Those are all different versions of the form 1 to infinity. So the question is, are they all the same answer? And based on what I've been leading you to believe, probably not. So that first one is the one we're going to investigate thoroughly today together. We're going to do it algebraically and prove that it's actually the definition of a really special number you're used to. This is E. This is its fundamental definition, or where it comes from. I'm going to show you algebraically in a second. You can, of course, check these graphically and see if you believe it, right? So I don't know what this one is, but let's see if it's also E using our calculator. You can do limits graphically as well as algebraically, right? Algebraically is the most important way, but let's graph these guys in our calculator and see what happens. So I'm going to put the first one in there, get these other functions out. So I'm going to go 1 plus 1 over x, I think that's okay, raised to the x power, and I'm going to zoom 6 to start out with. There we go. There's what that first one looks like. I really just want to look at this side over here on the right. You don't want to look at the other side. So we're just interested in infinity, right? Approaching infinity on this guy. Okay, so I'm going to zoom and make the window go farther because that's 10 is not close to infinity, right? Maybe I should go like out to 100 at least. I don't really need to go down into negative land, so that's probably good enough. Oops. Yeah, that's good. Okay, so there's my graph. Here it goes. Does it look like it's approaching some finite number?
Yeah.
Looks like it's getting pretty flat, right? So it's looking like as you approach infinity, there's some finite number it's approaching. If you wanted to calculate that, you could use your calculator lots of ways. You could look at 50, looks like 2.69. You could look at 90. If you want to look any farther out, you're going to have to, make your window bigger. So in fact, really, do I even need a picture of this guy? Can't I just go out on my home screen and go like this? And if I want to approach infinity, what should I chuck in there? Something really big. What's that look like? E. So that's definitely not a proof. We're going to do the proof here in a second. But it certainly seems like that limit goes to E, yeah? Let's look at the second one and see if it also goes to E or if it goes to something else. I don't know. So pretty easy to change. Just the only difference was this is a 3 now, right? So I'm just going to go back to my graph and see what happens. There's my graph. Whoa, it's like really steep. I better increase the Y. Come on, stop graphing. There we go. So better go up higher, maybe 500 or something. I think I went way up too much. You can see it graphing on the bottom there. It's way too much. Maybe I'll just go up to 100 or something like that. There we go. Now we can see it. Now the question is, just like the last one, does it look like we're approaching some finite number, or is it just growing slower and slower and slower? Sometimes it's a tough call. It still looks like it's growing slower to me. So instead of just plugging in numbers here, I'm going to go back out to the home screen and do this again. So if I put in 100, there's what I get. Put in a higher order of magnitude. And it's still growing, right? Fairly decent amount of growth. Still growing, but it looks like the growing is slowing down. Yeah, so I'm thinking the limit does exist. It's not just equal to infinity. Very much slowing down. But that means this has a limit, if you guys can understand that, yeah? So what is that number? It's 20 and change. If that one was E, and this one, the only difference is a 3, I bet it also has E in it. Maybe it's 3E? No?
E to the 3x?
What, Derek?
90.
Yeah. Good guess. Good guesses.
E to the 3rd.
There it is. So why is it e to the 3rd? But clearly you can see that, as expected, these indeterminate forms don't come out to the same based on whatever you got them from in the first place. So let's look at some basic L'Hopital problems before we go and deal with this one. So I'd like you to, by tomorrow, figure out what this one is with your calculator and then also confirm it with the new big approach that I'm going to show you in a second, okay? So that's one of the things I want you to do by tomorrow. You don't have to finish your assignment until Monday, and I don't think it's nearly as involved as those last couple assignments. It's going to go a lot faster, I think. I might be wrong, but I don't think so. Probably half the amount of time you guys have been working on the last couple, okay? But this one I want you to do by tomorrow. Okay, so let's go and just pull some problems out of the book and start slow. So back to L'Hopital. How about this guy? Some of these limits we might not even need L'Hopital on. I don't know. We're going to have to check. Not all limits you can L'Hopital. It has to be an indeterminate form of 0 over 0 or infinity over infinity, or you can't do it. Let's try that one. Let's try this one. And there might be other ways to do these problems as well. So let's Let's talk about those if we see them. I don't think we need our calculator again. Let's see. Let's do those ones to warm up. And I just pulled these straight out of the book. If you're getting confused in this section, the book is a great resource. It's got a lot more detail on the proof and the really logical parts of why L'Hopital's rule works. That's something you might want to look at. It's not necessary to use it. I mean, it's pretty easy to use. The book has a lot of really good tips and stuff in this section, quite good. And it'll continue to be like that through chapter 9, so it's a good resource. Yeah. Okay, so is the first one an indeterminate limit? Yes, why, Brandon? E to the 0 is 1 minus 1 is 0. Okay, so I always want to see this when you're doing L'Hopital stuff, just confirming that it's okay to use L'Hopital's rule. Once you know that, you can say that this is equal to the limit is still there, right? It doesn't go away. And you take the derivative of the bottom is 1, and you take the derivative of the top, which you guys are going to tell me is
2.
Right? And now you see, can I do the limit now? Well, that's irrelevant. E to the 0 is 1, so this is equal to 2. Done deal. You can check it graphically, no need to. Okay. X approaches infinity. Can anybody tell me the answer to this one right away? There's better ways to do this one besides L'Hopital, which we're going to review on Monday as well. Real quick, we'll do a tiny little lesson on Monday. You should just be able to look at that and tell me if you remember. Order of magnitude. Which one grows faster? X or natural log of X? X does. If the bottom's growing faster and you're approaching infinity, then you're going to get 0. Let's confirm it. We can use L'Hopital on this one too, because what are we going to get? Natural log of infinity is infinity. It might take a long time because it grows slow, but it'll get there. Obviously, it's infinity on the bottom. So yes, you can also use L'Hopital on it. So derivative of the top is what?
1 over x.
1 over x. Derivative of the bottom is 1. So really, I should probably write that as 1 over x. If you put something really, really big in for x and you keep going forever and ever and ever, that's clearly 0. Okay? So just some review. This guy, can we use L'Hopital on this guy? You put negative infinity on top, you get infinity. If you put negative infinity on bottom, e to the infinity is infinity. Yes, you can use L'Hopital. I should really probably put something in here that says I used it. So like right here, I'd put like this. Just why those are equal a little bit. Okay. So the top's derivative is 2x. Oh, what did I forget? Dang it. So 2x over negative e to the negative x. Stick that in, you get negative infinity over negative infinity. Another one. So now I'm going to say, all right, this is equal to, by another L'Hopital, limit, derivative, derivative. You guys are good, right? The good stuff's pretty easy. So, 2 over infinity, which is 0. So you can use L'Hopital multiple times in some cases. If it's an indeterminate form of 0 over 0, or infinity over infinity, you can keep doing it. Let's look at a new one. I didn't give you one like this from last year. I could have. I mean, it's not very hard. But I just didn't want to, do too much. So, what is this form? Just stick it on my desk. I can't get you right now. I'm going to have to come back. Okay. So, what is this if we plug in?
That's 0. Yeah, that's 0.
This is clearly infinity, right?
Well, that's the square root.
You say that's 0. Why, Derek?
Because it's basically 1 over e to the x.
It's 1 over e to the x. The other way to think about it, which I think I'd encourage you to remember, is what does e to the negative x actually look like as a function? Just from the library. There's e to the x. What's negative inside do? Horizontal transformation. As you approach infinity on this guy, unlike my graph looks, it goes like that, right? So it approaches 0. Derek's way is just as good, but that's something you should not forget. So the question is that 0? Is that infinity? Or is that somewhere in between? We don't know. It's an indeterminate form. So how do you do this problem then?
You derive it?
You can't use L'Hopital's rule unless it's 0 over 0 or infinity over infinity. The question is, can you use algebra to make it be one of those things? Well, yes. It's not very clever here. What can I do? It's what Derek did. I can say that's really just this. And that is this. In fact, when I look at this, I don't even have to use L'Hopital's rule. I just know the answer. The answer is going to be 0 because
It grows faster.
what grows
It's all
faster?
bottom.
Exponentials grow faster than square roots, duh. Let's confirm it just in case. So we could say yes, I could L'Hopital this. We already know the answer. It's just a little more evidence. So we'll say, well, that's equal to the limit of this. What's the derivative of root x?
1 half.
That, right? Derivative of e is e to the x. So I could write that as that, right? If you put infinity in now, that's infinity. That's an even faster infinity. So it's really just what we said all along. Okay, so that wasn't a very big variation on what you already know, right? Not much. Good to review, though. Let's do a new problem.
Teachers, at this time, please release the voice soccer players. Thank you.
I tried to get there, guys. So this is the big one. I'm going to watch that before tomorrow. Okay? All right, so this is what we just got. The answer was what a second ago? E. Y. This is 1 to infinity indeterminate form, right? So, based on looking at our calculator, we already know it has some limit. So, what you want to do is remember that it has a limit. And just assume that it's going to work out to something. Let's call that something y. You could call it L for limit or whatever. It's traditional to call it y. Now, that x up here is what's really causing me problems. Isn't there something that lets you, like, bring x's down? Logarithms. This is now an equation, right? So what can you do to equations? You can operate on them with things like logarithms. So now this is probably the weirdest step. This logarithm, because this is a continuous function, if you guys saw it a second ago, it was nice and continuous, straight, not disconnected or anything like that, at least out to infinity. There was this property back in the day, which you don't really need to remember very well, that said if it's a continuous function, you can pass a logarithm inside of a limit. So that's kind of weird. But you can pass a logarithm inside of a limit as long as the thing inside is continuous. And now, one of the reasons we picked a logarithm to operate with was because that x can now go where? front, I'm not even going to touch this limit thing until we simplify it a lot more. So now this x is coming down in front, so we've got x times the logarithm of 1 plus 1 over x. And then we've got some stuff over here that is not going to be touched just quite yet. Now, is that an indeterminate form? Let's check, because if it is, what can we use? L'Hopital. Infinity. What's this become if you plug in infinity? 0, because why, Gabe? Because it's the natural log of 1, right? So that'd be 0 times infinity. That's indeterminate, but it's not L'Hopitalable, if you want to turn that into a verb. Yeah? So the question is, can we use some clever algebra? I think it's a little bit clever, but not too clever, to make this into, instead, 0 over 0, instead of what it is now, which is infinity times 0. This doesn't, you don't have really a lot of options with this, right? It's a logarithm of junk. So, yeah, I don't think you want to do anything with that quite yet. But x is x. You can do all kinds of things with x. If you want it to instead be division instead of multiplication, what could you do?
Can we just divide by x to the negative 1?
Yes, something like that. If instead of writing it like that, what if you wrote that x like this? Is that still the same thing? Yeah, because you could flip it and put it back up there, right? That's not super clever. It's a little bit clever, but it's not that clever because we know we're trying to get 0 over 0 or something like that, right? So now we can L'Hopital this because it's 0 over, yeah, 0, natural log of 1 is 0, check. So we can say by L'Hopital, guess I'll stick it in red here, right here, that this is equal to what? Can you guys help me with the derivatives? Remember, this is x to the negative 1. What's the derivative of x to the negative 1?
X to the negative 2.
So this is going to be negative 1 over x squared, right? Then we got to take the derivative of this, which is a little bit more involved. What's the derivative of natural log? 1 over stuff. I wrote the stuff a little differently, right? And then we're going to have to take the chain rule of the stuff. Didn't we just do the chain rule of that, though? So I'm going to put it in a different color. That's really just another one of those, isn't it? So it cancels out. Nice. It's key here is that this part is now going to go away. So now what do we have? Remember, don't forget the other side. We've got a natural log of y over there from operating on both sides of this equation. And on the right-hand side, I have the limit as x approaches infinity of what's left. There's no logarithm anymore. That, right? The only reason I wrote it like this in blue is so we could see the derivative again, so I could put it there in red. Yeah? Is that something we can do?
Yeah.
Yeah. Infinity put here makes this part
0.
go to 0. I like to write that like this. I'd encourage you to do so as well. That'll help you out, okay? That part goes to 0. What's left, though? Limit of 1 is 1. The limit of this one is 1. This is really just 1. And we wanted to find the limit all along. What did we assume the limit was called? Y. How do you solve for y?
E to the y.
Now you know where E really comes from, I think. It's been becoming a long time, right? So it's from using L'Hopital and a little bit of clever algebra to mess with an indeterminate form of a function. That's where E came from in the first place. People started working with E a long time ago, even before they really understood this argument, because it just came up so often, and because, you know, Isaac Newton was aware of E because it was that special thing that when you took its derivative, it was just the right slope that it became its own derivative, right? That we had discovered last year. So people were working with E for a long time before they ever even came and mentioned this. But let's do it one more time, the same kind of argument on a different problem. So one last question for today. This is called logarithmic limits. It's just another way to work with tricky indeterminate forms, so don't think of it as like some big machine. So let's see, there was one more question I wanted to look at. Last one. What really tells you that logarithmic excuse me, limiting might be necessary is really strange indeterminate forms. What's this one? Let's just check it out. If we put 0 into sine of 0 is 0, and then 0 power, this is 0 to the 0 power, is that 1? Well, all other things raised to the 0 are 1, but not always this one. This is indeterminate, undecidable. So how did we do it last time? We could, of course, check on our graphing calculator and see if we believed it had a real limit. But let's just say we assume it does. Maybe it won't. But something strange happens, we'll have to back up and look. Okay? Next step, you guys tell me. Log both sides. This is a one-sided limit, right? Next step. Pass the logarithm inside the limit. That assumes that this function is continuous. We don't have any reason to believe that. We'd have to check it, but let's just assume it for today, okay? So we can move on. We could look at it in our calculator or decide some other way that it's continuous. And then we're going to bring that x down in front. I'm just going to do that in the same step. Okay? And now, you guys help me with the next step. Say again, Gabe? And now see if that's L'Hopital. Well, I guess we could have checked right here. This is 0 times the natural log of sine of 0 is 0. Well, let's see. If we put 0 in there, remember we're approaching from the right. This is a one-sided limit. So we'd have 0 times the sine on the sine wave. If you go like this, you approach it from the right, it's 0, so that's natural log of approaching 0. If you actually have the natural log of 0, that's undefined, right? But this is approaching from the right. If you approach on the natural log graph from the right, where do you get to? That's 0 times negative infinity, which is another indeterminate form we can't handle. So that's why we use this clever algebra trick to turn it into something we can handle. This is instead 1 over something really close to 0 from the right. So 1 over like 0.0000001. What's 1 over 0.0000001? Really big. It's infinitely big, right? You divide 1 by something really small, you get a lot of stuff. And then this guy we just thought about, if we thought about that, it's going to be negative infinity. You can use L'Hopital on negative infinity over infinity, that's okay. Yeah. So, time for L'Hopital. So we're going to come in here and go L'Hopital. We've now got the natural log of y equals what? We just did this one a second ago.
Over cotangent.
Cotangent? Where's Katie pulling cotangent?
The integral of cotangent is
Derivative.
another. Oh.
Oh, you're thinking
Oh no, I was
backwards.
thinking the other way around.
Okay, well she's right, right? 1 over sine times cosine. Cosine over sine is cotangent. So you could write that out if you wanted to. I'm going to clean this up before I even do anything else. That's the limit. So you approach 0 from the right of, let's flip stuff, shall we? because this is up there, because it's negative exponent, right? So you can flip it. What's cotangent flipped?
Tangent.
Tangent. Before even doing that, I mean, you could try to stick this in again. That's fine. Let's just try to stick it in this though. So if I do this, I'm going to get 0 over tangent's graph looks like this, of course. As you approach it 0 from the right, you're going to get 0. So what do I need to do? L'Hopital again. So by L'Hopital again, I'm going to get negative 2x over secant squared. Now I can try it again. That's going to be 0 over secant. Secant looks like this, right? So you approach 0. Oh, that's going to be something. It's going to be, in fact, 1. So I think that is 0. Does that make sense? There's the graph of secant. How did I get this graph quickly? Because I said cosine. Cosine has that middle hump, right? Okay. So it's not 0 is the answer, though. We have the natural log on the other side, so don't forget about that. That's tricky. So we have basically the natural log of y equals 0. So e it, and you get 1. This limit goes to 1. Kylie, you okay? So we got that side to be 0. The other side we have natural log. So e it, you get 1 in this case. All right, I think that's it for today.